Hi everyone, in this video we're going to talk about kinetics and the second part of our unit where we look at collision theory and reaction mechanisms. And in this lecture we're kind of examining what really causes reaction to happen. In other words, we've previously only really looked at the beginning and the end of a reaction. We go from reactants to products without really considering what the intermediate steps are. And so the two subtopics we're going to look at here, one is collision theory and the other is reaction mechanisms, will give us a better understanding of how reactants really do get transformed into products. So first of all, we want to talk about the central theory here, which is that in order for reactant molecules to turn into product molecules, we reason that a collision needs to take place. We know that all particles have at least some kinetic energy, even in the solid phase at low temperatures, and that a collision needs to take place in order for a reaction to occur. It's not unusual, like it says, for there to be billions of collisions per second. And when reactant molecules actually collide, they may or may not actually react. There are two factors we need to consider. One is whether they've collided with sufficient kinetic energy, and the other is whether they are properly oriented. So we'll look at each of those two conditions. Now, if those two conditions are satisfied, then we have what we'll call an effective collision, and that can lead to a product being formed. And of course, if there's a high frequency of effective collisions, then we're going to have a high reaction rate or a fast reaction rate. We also want to introduce another important term here called the activated complex. When two molecules do have an effective collision, then you'll form this high energy or very unstable species that's sort of a transition state between reactants and products. And in that transition state, the bonds in the reactants are not completely broken, but the bonds in the products have not yet completely been formed. Here's the first requirement that we're going to look at, and that is the requirement that the colliding particles have sufficient kinetic energy. So in this reaction, you can see the equation at the bottom of the slide. Nitrogen monoxide and ozone are reacting to form NO2 and O2. And at the bottom of that picture, you can see some particles of ozone, O3, and NO colliding with insufficient energy. So there's no reaction that occurs there. But at the top of the picture, you can see that sort of conglomerate, which I guess represents the activated complex we were talking about before. Those three that have the really bright, sort of fiery looking lights coming off of those, that's sort of the transition state where the collision has occurred with sufficient energy, and you can see the product molecules are also shown emerging from there. That is what we call the activated complex, when an effective collision has occurred. And in order for that to occur, you need a sufficient activation energy, which is given the symbol E sub A for energy of activation. So that's the kinetic energy requirement. A lot of the time we'll look at an energy diagram like this one, which shows potential energy on the y-axis against time or reaction progress, or reaction coordinate is sometimes how these x-axes will be labeled. And you can see there's sort of a hill or a peak that represents the activated complex at the top. And in this particular case, the reactants actually have a higher potential energy than the products, and we'll talk about the fact that that means this is an exothermic reaction. But more importantly, you can see that there's an energy barrier that is represented by that activation energy. And it's measured from the relative potential energy of the reactants to the potential energy associated with that activated complex. After that activated complex has been formed, then the reaction is committed to roll down the hill, so to speak, and the bonds of the products will finish being formed. The second requirement we'll look at is that of proper orientation. So in this example, you'll see at the top a molecule of NO with the O side facing the central oxygen in ozone does not lead to an effective collision. And if the N side of the NO molecule hits the central oxygen in ozone, it does not lead to an effective collision. If the oxygen side of the NO molecule hits that acute angle in the ozone molecule, that does not lead to an effective collision. It's only if the nitrogen side of the NO molecule collides with that acute angle in ozone that we form that activated complex, and that makes sense since NO2 is one of the products. We can maybe reason that that is a sensible orientation to be required. Here's another example of a reaction that illustrates this requirement of orientation being necessary for an effective collision. There are two molecules of nitrosyl chloride that are reacting to form chlorine gas and other products. But since chlorine gas, diatomic chlorine, is a product, it maybe makes sense that the two chlorine atoms have to combine in order for the collision to be effective. So those two requirements, in summary, are the sufficient kinetic energy and the proper orientation. And again, to summarize our vocabulary here, the activation energy is the amount of energy needed to get to that transition state that we call the activated complex. And that is a state where bonds are neither formed completely nor broken completely. It's a very high energy state. And the dotted lines that are shown in this diagram are probably a good illustration of how we could visualize that transition state. We'll take a detour here for a minute and talk about change in enthalpy, since the diagrams that we're looking at will often label the energy that's released or absorbed in one of these reactions and refer to it as change in enthalpy, or delta H. And if you haven't already studied enthalpy, then for now you can simply think of that as the change in heat content of a system. So if you look at these two reaction coordinate diagrams, you'll see delta H and EA, activation energy, are labeled. And we want to be able to recognize how these are defined and be able to label these on a reaction diagram of this nature. Here you'll see that in both cases the energy of the products is lower than the energy of the reactants. That means we're talking about an exothermic reaction. In the one on the left, we have a very small activation energy, and on the right a very high one, but they're both exothermic reactions. Let's talk a little bit about how we can determine that. If the change in enthalpy is positive, in other words, final minus initial, or products minus reactants, gives us a positive number, then we're talking about an increase in internal potential energy of the system, or an increase in the heat content of the system. And that means energy is flown or flowed from the surroundings to the system. That would be an endothermic process. But in the other example we were looking at earlier, and in the example in B here, the energy of the products is lower than the reactants, so that would be a negative delta H in an exothermic process. So just to summarize about this quick detour we took, make sure you can label delta H and energy of activation on these diagrams and distinguish exothermic from endothermic processes. Any other discussion of enthalpy will be reserved for a unit on thermochemistry or thermodynamics, but it is relevant to these diagrams, so we want to include it here just to that extent. So we'll talk about the second topic now, which is that of reaction mechanisms. And reaction mechanisms really are a closer look at those in-between steps. Now that we understand that collisions are necessary, effective collisions are necessary, we now want to take a look at what some of the in-between steps between reactants and products are. After all, we've so far just described the beginning and the end, and we haven't talked about the middle of the story. And most reactions don't just involve one step, but instead involve a series of smaller steps, which we're going to learn are called elementary reactions, or elementary steps. And usually those involve just one or two molecules, sometimes, rarely, 3 molecules. And we're going to describe mechanisms, which are a series of steps that produce the overall reaction, those elementary steps. Now, these are determined semi-empirically, since you can't observe them directly, and we're using experimental data as well as just reasoning about chemical principles to propose reaction mechanisms that are plausible. If we know the overall reaction rate, or the overall rate law, that can help us deduce what possible reaction mechanisms are. So let's take a look at some of these examples. The first example we'll look at is this overall reaction between hydrogen and iodine monochloride, that's ICl. And the proposed mechanism is that first, in the first elementary step, a hydrogen molecule combines with an iodine monochloride. molecule, ICl, and produces hydrochloric acid and hydroiodic acid. And then in the next step, hydroiodic acid combines with another molecule of ICl to produce hydrochloric acid and diatomic iodine, the products of the reaction. So these are elementary steps labeled 1 and 2 there, and they cannot be broken down into further steps, right? These molecules actually interact directly in that manner. And this mechanism that's proposed says there's 2 steps. Now, looking at those 2 steps, you might recognize that HI, hydroiodic acid, that is not a reactant or a product in the overall reaction. We call something that's produced in an early step and then consumed in a later step an intermediate. And it's important that we recognize intermediates in reaction mechanisms. Those are materials, again, that are produced in an early step and then consumed in a later step. And in this case, HI is an intermediate. If we add those 2 equations together, you'll see that not only does HI cancel out, but the overall reaction, which is given in that teal colored equation at the top, is given by adding the 2 other ones together. When we look at elementary steps in a reaction, we will talk about what we call their molecularity. The molecularity is determined simply by the number of particles that are colliding. If we have just one reactant molecule in an elementary step, then we say that it is a unimolecular step. If it involves 2 particles colliding, even if they're the same type, we call it bimolecular. And if there are 3 molecules colliding, and you can imagine that for 3 molecules to simultaneously collide right in the same instant, that would be pretty improbable. We'd call it a termolecular step, but those are so exceedingly rare that any mechanism that suggests a termolecular step is usually viewed with skepticism. I explained before that each step in a mechanism is its own little reaction with its own activation energy and its own rate law, but these cannot be further broken down into smaller steps. And so unlike overall reactions, whose rate laws must be determined experimentally, you can determine the rate law for an elementary reaction directly from its molecularity. And you can see that I've done that here for these 2 steps. The first elementary step involves just one collision between H2 and ICl, and so the rate law is simply K multiplied by the concentration of those 2 species. Since there's just one molecule of each colliding, they're both raised to the first power, and I can write a rate law directly from the molecularity of that equation. Again, be careful. You cannot do that for an overall reaction. Rate laws for overall reactions must be determined experimentally. But for the second elementary step, we can also write a rate law, and you can see the rate law for the second elementary step is going to come from the fact that it's bimolecular, just a collision between an HI and an ICl molecule. So here's a summary of how I was able to do that. If there's only one reactant, then we say it's unimolecular, and the rate law is very simple. The concentration of A is going to be multiplied by the rate constant. In the second row there, you can see if 2 molecules of A collide, that's bimolecular in A, and the rate law is K multiplied by concentration of A squared, and so on. Notice that if we have 3 molecules simultaneously colliding, that would be very rare. And usually, like I said before, that kind of a mechanism would be viewed with some skepticism. So there's a summary of the different molecularities we're going to examine. Unimolecular, that would mean a first order reaction. Bimolecular, that would mean a second order elementary step. And termolecular, that would mean a third order elementary step. When we look at reaction mechanisms with multiple steps, there will always be one step that occurs slower than other steps. The result is that that slow step is going to limit the rate of the overall reaction. Products can't be produced any quicker than that slowest step will allow. And the illustration here shows that even though there might be one strip of the highway where 3 cars can pass per minute, In that construction zone, wherever or only one car can pass per minute, that's going to be the part that limits how quickly cars can arrive at a destination. So we call the slowest step in a mechanism the rate determining step, or RDS for short sometimes. It's going to be the slowest step because it has the highest activation energy, and effective collisions are going to be infrequent. The rate law of that elementary step is going to determine the rate law of the overall reaction. So here's an example we'll look at to see how the rate law of an overall reaction can be reconciled with a possible mechanism. Here's a proposed mechanism for the overall reaction given at the top of the page. Now, there's one step here, which is indicated as the slow step. It's the first step of that reaction. And that last number 2 there should be a superscript. You can see that the slow step is bimolecular in NO, and that means it's, bimolecular in NO2, which means that it's going to involve the collision of 2 NO2 molecules. That is the slow step, therefore it is the rate determining step, and the experimentally observed rate law should match the rate law for that elementary step. So we should be able to predict what we'd see in experiments. It should match the rate law of that slow step, and again, that number 2 should be a superscript. If we did an experiment to measure the observed rate law and we found that it did not in fact match this form, then we would reject that as an invalid hypothesis. Alternatively, we might be given the observed experimental rate law and a proposed mechanism and be asked to evaluate which step would be the slow rate determining step, step 1 or step 2. We'll look at examples like that a little bit later. Before we move on, I want to come back to our reaction coordinate diagrams and show how the mechanism can be depicted in these diagrams. And you'll see there are 2 barriers, there are 2 peaks there, 2 energy barriers for this reaction to overcome in order to reach completion. And the first one is the higher activation energy, and that is consistent with the idea that the first elementary step in our mechanism was the rate determining step, or the slow step. The reason it's the slow step, it has a higher activation energy. Notice how the activation energies are measured in each case, and you can also see labeled that other idea we talked about before, which is the enthalpy of the reaction. So a 2-step mechanism can be modeled in this way, and a 3-step or even more multi-step mechanisms can be shown in these energy diagrams, and the number of peaks that you can recognize indicates the number of elementary steps that the mechanism is suggesting. So we'll often be asked to validate a mechanism, and in order to validate a mechanism or show that a mechanism is plausible and consistent with an experimentally observed rate law, not only do the elementary steps need to sum to the overall reaction, but the rate determining step in the mechanism needs to be consistent with the observed experimental rate law. So let's look at each of those 2 requirements to validate a mechanism. First, how can we add up the individual steps to give an overall reaction? Here's an overall reaction which is given in the decomposition of dinitrogen pentoxide. Let's see if this mechanism meets that first criterion. Do those 3 steps add up to the overall reaction? Well, I see that the overall reaction involves 2 molecules of N2O5, and this mechanism shows them only appearing once, so I'm going to start by doubling that. And we'll see that many other things are canceling out. The intermediates, which we talked about before, include NO3. Notice NO3 is not appearing in the overall reaction, and as a matter of fact, neither is NO. And NO is another intermediate we can cancel out. So with that number 2 applied as a coefficient to everything in the first step, then we'll see that in fact all of those reactants add up to the 2 N2O5 molecules in the overall reaction, and all the products also add up to give the total number of molecules in the products of the overall reaction. So that criterion is met. We want to make sure all the elementary steps add up to give the overall reaction. The second condition we want to make sure is met is that the rate law predicted by the mechanism is consistent with the rate law we observe in the lab. So let's look at that as an example. Here we have a reaction A plus 2B yields C, and the slow step is identified as the rate limiting step. Let's write the rate law that's predicted by this mechanism. Let's see. First, we want to identify the slow step as the rate limiting step. And since it's bimolecular, involving just a collision between A and B, then the rate would be dependent only on that slow step. And you can see it's given by that bimolecular nature of that first elementary step. If we experimentally observed a rate law that was consistent with that, then we would reason that this mechanism is plausible. Those are the two requirements for making sure a mechanism is plausible. We'll look at one other idea here which emerges when a mechanism has an early fast step. So when the early steps are not rate limiting, then there can be sometimes a bit more of a complicated solution to determining the rate law from the mechanism. The problem is that our rate law really should not contain intermediates. And if we have a slow step being like the second or third step in a reaction, it's likely that that slow step will contain some intermediates, which we don't really want to include in our rate law. To avoid including intermediates in the rate law, we're going to substitute the reactant equivalent of that intermediate from the earlier step, assuming that its concentration is present in a steady state of equilibrium. And this will require a little bit of explanation of equilibrium and some other ideas and examples to illustrate. If we look at the last example and modify it by flipping the order of which one was fast and which one was slow, and if we're asked to write the rate law for that mechanism, or the rate law that's predicted by that mechanism, we have a bit of a problem. The slow step is D plus B, but I can't write a rate is equal to K times the concentration of D times the concentration of B, because D is not even a reactant in the overall reaction, right? I can't include D, that's an intermediate. So I have to think about how we can overcome this problem. And there are some approximations and tricks that chemists use to avoid including intermediates in reaction mechanisms. We're only going to look at one, which is called the steady state approximation. Since a rate law should not contain that intermediate D, we're going to substitute the equivalent of D in the earlier equilibrium step, which is A plus B. And that's because the reactants and products are in equilibrium in a steady state, and so are essentially equivalent. Now, if I do that, then substituting A plus B for D in the slow step, then I get a rate law like this, and that would be the rate law that's implied by this particular mechanism. First order in A and second order in B overall. Using this steady state approximation is a tricky thing to follow the logic behind. There are a few caveats I can give. In AP chemistry, if the early steps are fast, then they'll be indicated as equilibrium steps, either by that double arrow or the words fast equilibrium. And that allows for that steady state approximation. I want to walk through a proof of this approximation, and it says, although you will not need to perform such a calculation, it will be important to understand. As a matter of fact, you may be asked to perform similar calculations to this one. So let's take the time to go through this as one last idea in this presentation. Here's the overall reaction we're going to look at. It involves hydrogen gas and NO reacting. You can see that it's first order in H2 and second order in NO. Here's the mechanism that's proposed. Notice the first step is a fast equilibrium step. I've also included above and below that double arrow The symbols K prime and K negative prime to indicate the rate constants for the forward reaction and the rate constant for the reverse reaction, respectively. And that second elementary step is the slow step, which is the rate limiting step. If I wrote a rate law for that rate limiting step, then I see it involves N2O2. And N2O2 is neither a reactant nor a product, it's an intermediate. So that would be an invalid rate law. What to do when your rate law includes an intermediate? We're going to see if we can use this steady state approximation. Here's how it works. Since that fast early step is an equilibrium process, that means the forward rate and the reverse rate are equal. And I can write a rate law for the forward rate, that's given there, and I can set it equal to the rate law for the reverse rate, which I've also given. Notice the two rate constants are actually different values, since one of them is K prime, one of them is K negative prime. And now I'm going to use that equality. I'm going to use that equality to solve for the intermediate, the concentration of N2O2. So since the forward rate and reverse rate are equal, I can rearrange the equation to solve for the concentration of N2O2, and I get this new term in the bottom right there, K prime over K negative prime times the concentration of NO squared. That can be substituted now into the slow steps rate law. So instead of writing N2O2 in the slow steps rate law, I'm going to substitute that value which I just derived. And I see I can simplify that by just taking that complicated piece of constant machinery there and replacing it with a new value of K, right? That new K value is the overall rate constant for the reaction. Notice that actually matches the observed rate law that's given there in green, and it does not contain any intermediates. That's how we'll use the steady state approximation when there's an early fast equilibrium step. So that wraps up an introduction to collision theory and reaction mechanisms.